And welcome back, ladies and gentlemen. What we want to take a look at today is section 3.5, graphing techniques. We're going to take a look at transformation stage. So one of the previous videos, we took a look at the library of functions and all the different functions that we should be somewhat familiar with. And now what we want to do is we want to go ahead and move these functions around. And how are we going to do that? We're going to take a look at horizontal and vertical shifts. In other words, can we move the graph up and down and right and left? Another thing we're going to do is can we compress and stretch the graphs? So what do these kind of take a look at as we do those? Whoops, the screen kind of blanked out for a moment there. And then the last thing that we want to be able to do is go ahead and reflect things over the x-axis and reflect things over the y-axis. So what we've looked at before was symmetry. We're now going to kind of create on our own as far as definitely reflecting them over the x and the y-axis. So we're going to take a look at some things in Desmos. We're also going to take a look at just some other basic graphs here and whatnot. So let's start off with, on a graph utility, it says graph the following. So letter A, if we go ahead and graph f of x is x squared, f of x is x squared plus 2, and f of x is x squared minus 2. Okay? So overall, if we take a look at the graph of f of x, we already know that from the parent function, or the library of functions, it should look something like this. So now the question is going to become, what happens when I put this plus 2 at the end of that? So if I would have a table of values here, okay, where I end up with x equals f of x is x squared, I know that I go by normal values, and I get 4, 1, 0, 1, and 4. What happens then if I take a look at this and extend this out and I say, what if I want x squared plus 2? And what's going to take place in this regard? So really what we see then is the x squared is the value in this second column. What we're going to do is add 2 to that. So we're going to make that 6. We're going to add 2 to that 1, make it 3. Add 2 to the 0, make it 2. Add 2, make that 3. Add 2, make that 6. So what we anticipate happening then is that overall this graph is just going to be the same graph. We're just going to move it up 2 spots from every place that it was before. Likewise, what we anticipate happening then is if I say, what if this is x squared minus 2? Well, again, the x squared was all the values in this first column. So now if I want to go ahead and subtract 2 from each of those, then if I take 4 minus 2, I should get 2. 1 minus 2 is negative 1. 0 minus 2 is negative 2. 1 minus 2 is minus 1 again. 4 minus 2 is 2. So it looks like all of these y values end up getting shifted down 2 spaces. And what I could have done here is go in this direction, they ended up getting shifted up 2 places. Okay, and so if I go ahead and finish this out here, these values here should have gone down to overall general concept idea. Let's take a look. So that's the idea that we think should happen as we go through these. Let's go ahead and take a look then at Desmos and see what actually does happen. So pop out over here into Desmos. So we have our x squared, and we see, okay, that's our standard graph that we expected. As it goes to the origin at 0, 0. We have a point here at 1, 1, and negative 1, 1. Kind of scooch down there a little bit. And then we also, if I move this down over here, at 2, we've got 4. At 3, we've got 9, those values. And we have the other side as well. If we add 2, what I'm anticipating happening is this graph should move up 2 spots. So if I put that in there, we do indeed have that idea. So this is 0, 0 now moves up to 0, 2. This 1, 1 now moves up to 1, 3. This 2, 4 now moved up to 2, 6. So we get the idea that it does indeed seem to be moving upward. If I go ahead and put the minus 2 on it, now in the purple, looks like from our original in blue, if I put a minus 2 at the end of it, now every single one of these values now has dropped 2 spots. So I did have 0, 0. Now we've got 0, negative 2. I did have 1, 1. Now we have 1, negative 1. Then we had 2, 4. If I drop down 2, now we've got 2, 2. Same way on the other side. So it does seem to hold true then that the thing that we were referencing in this regard was that these plus 2 and minus 2 ended up shifting vertically. And that's one of the major components that we want to take a look at in this particular spot. Let's pull this back up here. Is that anytime we have something outside of that function, okay? So anytime we have something outside the function, so if I have the overall function f of x, if I go ahead and put a plus something at the end of it, okay, that is going to end up moving it. If it's positive, going to move it up. And if it's negative, I'm going to end up then moving it down. Okay, and so this plus k, assuming k is positive by itself, whatever we're adding is going to move it in the upward direction, and anytime we subtract, we're going to move it in the negative direction. So this is what we call a vertical shift. And like when we did our circles, if you remember on that one, we had x minus h quantity squared plus y minus k quantity squared equal to r squared. This k affected the y value, yes? It's the same thing. We carry that same kind of idea all throughout. Let's take a look at another example here. Let's do the square root function. So as we take a look at the square root function then, g of x equals the square root of x. Then we're going to do the square root of x plus 2, and then the square root of x minus 2. And then we're going to see, okay, what happens then in my general g of x if I go ahead and do the x plus h in parentheses, the x minus h in parentheses, different from what we had up at the top here, or this first example, letter A. We had what we were doing, adding, subtracting, was outside the parentheses. Now, what we're going to do, all of these things are inside the parentheses. So when it's inside the parentheses, it's working off of x. Okay, so now it's going to affect x. Whereas if it's outside of the parentheses, what that did is it affected the y values. So we want to be able to affect the x's in this regard. So this is going to be a horizontal shift. Notice again, same way as what we had looked at before when we did circles. In the circles, this h was the horizontal, the x value of the center of the circle. And so we moved right and left. Same thing down here. We're going to end up moving right and left again overall. So let's go ahead and take a look at our function in Desmos and see what that looks like one more time. So I'm going to minimize this one. Let's go down to example B here. So g of x, this is our square root function. And in our square root function, of course, we know that we're not evaluating anything less than 0 in the negatives because the square root of a negative doesn't make any sense. So we start at 0, 0. That's where we start with our domain for the square root function. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. Keep moving out, square root of 16 would have been 4. And so we can go ahead and take a look at those values that we're familiar with. So what I'm suggesting then is we do this x plus 2 and this x minus 2 underneath the parentheses, so it's in the function itself. It should be moving us right and left. Okay, let's see what this plus 2 does. So when we do this, part of the question is this going to move as far as this x plus 2? Because it's a plus 2, is this going to move us 2 to the right, or is this going to move us 2 to the left? Let's take a look. Oh, move this 2 to the left. Okay. Here's one way that we can think about this, and this is true all the time with our x values. Okay, anytime we're working with the x's, we tend to do kind of the opposite of what it says to do. So if we're doing x plus 2, instead of thinking, oh, I should move to the right 2 because that's what we're doing to the x, we end up shifting left 2. One reason, or one way I have figured out how to explain this to students that kind of gets a chuckle out of people and makes some sense is if you break up with somebody, or you know somebody who's broken up with somebody, either dating or a spouse or anything of those sorts, of, even just a friend, whatever your ex is doing, you don't want to be there, so you want to do the opposite. So if with x we're adding 2, we're going to go ahead and do the opposite. We're going to get away from them. We're going to go to the left 2, and that's what happened here. Likewise then, on this example down here, we have x minus 2. If it says to subtract 2, instead of going to the left, we're going to end up going to the right. Let's go ahead and check this, and we see that it does hold true. So all my values ended up getting moved to the right 2 positions. So anything that we work with the x's, think about doing the opposites. Let's go back to our screen over here. And as we take a look at this, one thing that we will end up doing in some of our paper pencil work is we'll say, okay, let's take a look at our function here. So we've got x and then the square root of x. So I have 0, oops, not negative 1, 0, 1, let's say square root of 4, square root of 9, square root of 16, etc. So these values I can do. And then we say, all right, what are we doing with this? Okay, so if I want to take a look at this as now x, and then say I want the square root of x plus 2, what should happen, because I've got this plus 2 in here, is this is going to end up shifting 2 places to the left. So if I'm going to do 2 places to the left, what's going to happen to my first position here as far as my 0? I'm going to subtract 2. So I'm going to subtract 2 there, and it's still going to end up being 0 because negative 2 plus 2 is 0, and the square root of 0 is 0. At 1, if I subtract 2, I'm at negative 1. So negative 1 plus 2 is 1. The square root of 1 is still 1. If I subtract 2 from 4, I get 2. And 2 plus 2 is 4. Square root of 4 is 2. If I subtract, what are we doing? Subtracting 2 from the 9, we get 7. 7 plus 2 is 9. Square root of that's 3. 16, take away 2 is 14. Oops. Yeah, so 14. And then 14 plus 2 is 16. Square root of 16 then is 4. So one of the things that we see happening here is we note these, is I've got my x values. And so what I did here, let me do it this way. I subtracted 2 from each of those x values. What happened to all my y values here, though? All my y values stayed the same. So the only thing that changed on these were the x's. Okay, and one way that we might show this paper pencil is doing something like this. We don't need all the arrows in here. We might just do something like this and then put that down in and say, we're going to shift this over 2 to the left. Let me clean up my writing here. So we're going to shift 2 left. Just recognize as I was reading that side, man, that's not very clear. Okay. So that is our horizontal component. So what have we done so far? We've taken a look at vertical. So whatever the vertical says to do, that's how we shift it. It was plus 5, then we go up 5. It's minus 5, we go down 5. In our horizontals, though, we just do the opposite. So if it says plus 5, we really go left 5. If it says minus 5, then we go to the right 5. So these end up shifting from each other overall. Let's take a look at another example. What if we do combinations? Let's squeeze this back in here all the way. There we go. So what do you think combinations of H and K will do? Well, if H moves us horizontally and K moves us vertically, if we have something that says X plus 3, instead of this case, so the parentheses are grouping symbols, they're absolutes, and then minus 5 outside, whatever is with X is going to move it horizontally. So this should end up being, remember, we do the opposite of what it says when we do with X. It should go left 3, and then we have a minus 5. So that means that's a vertical. So minus is negative going down, so we should end up going down 5. So from our base absolute value function, let's do it this way. Get rid of that one. For our base absolute value function, we did this in the family of functions. We've got this nice V shape. What we should see happen then is we should go move everything to the left 3 and down 5. 1, 2, 3, 4, 5. Should be over here. And that's what's going to happen to our graph overall. Now, of course, we can clean this up a little bit more. Take a look at it in Desmos and say, hey, how does this look in a much cleaner format? So let's go ahead and take a look at that one. So there's my absolute value of X. It is indeed the nice V shape that we're looking for. If I take these one piece at a time, the plus 3 inside the absolute value bars, it does end up moving 3 places to the left. If I do just minus 5 outside the bars, that's affecting the y value, and we see it does move this 5 places down. If we put these together, so 3 places left, 5 places down together, we move 3 left, 5 down, and there's our new graph. Okay, so hopefully that makes a decent amount of sense to us. We'll get to the vertical stretch compression in just a second. I want to move that out of the way, because one other thing I want to take a look at, one of our paper pencil assignments will go ahead and ask us, well, what do we do at this point here? How does this point change? Because this is 0, 0. That was the bottom of our V. It's going to end up being -3, -5. How do we show that without doing all the graphs? Go back over here. And as we take a look at that, we're going to say, all right, let's take a look and start with x. Excuse me. Start with x. And let's just do the parent function. Let's do absolute value of x. So our normal values we do are -2, -1, 0, 1, and 2. Absolutes. Remember, we take the positive of those values. And it doesn't matter which one of these we do first. I normally like to do these, and it's generally prescribed to do it in the order of operations. So order of operations, we do what's inside any grouping symbols first. If you remember, the way that we remember this is, please excuse my dear Aunt Sally, or PEMDAS. This P for parentheses also generically should be any grouping symbol. So whether that is parentheses, absolute value, whether they're the curly braces, the square braces, square root symbol, any of these we do first as far as our order of operations. So let's see what happens then. So let's do x, and then let's do the absolute value of x plus 3. So what we're doing on this one overall is we're recognizing that we're moving 3 left. Okay, so if I'm moving 3 to the left, -2 minus 3 should be -5. -1 minus 3 is -4. 0 minus 3 is -3. 0 minus 1, -2. 2 minus 3 is -1. Now, theoretically, what should have happened then? We only changed the x-coordinate. So that means my y-coordinate should remain the same as 2, 1, 0, 1, and 2. Let's double check those. So let's go back into our absolute values. So now we've got up here absolute value of x plus 3, but now x is -5. -5 plus 3 is -2. Absolute value of -2 is 2, just like we thought it should have been. Plug in -4. -4 plus 3 is -1. Absolute value of -1 is 1. Plug in 3. -3 plus 3 is 0. Absolute value of 0, still 0. -2 plus 3 is 1. Absolute value of 1 is 1. -1 plus 3 is 2. Absolute value is 2. So we do see what we expected to as far as showing algebraically what's taking place. If I move 3 to the left, I want to move 3 places to the left so that my y values end up still being the same thing. Now let's take our x values, and we'll do x plus 3 minus 5. So now we're going to do the 5 down. Okay, so 5 down, that should affect the y values. So if that affects the y values, my x's are going to end up remaining the same. So I'm going to leave my x's as -5, -4, -3, -2, -1. Now I'm going to go ahead and subtract 5 because I'm not changing the x's. So this piece here is what all of these values were. So I'm going to go ahead and take that -5, I was at 2, now subtract 5 more. If I subtract 5 more, I'm at -3. So basically what happens, we took 2 and we subtracted 5 to end up with -3. I could plug this -5 back in. -5 plus 3 is -2. Absolute value is +2. +2 then minus the 5 was the -3. Same idea with negative 4. I could plug it in. Negative 4 plus 3 is negative 1. Absolute value is 1. 1 minus 5 is minus 4, so negative 4. Or I could have just taken this 1 from what I knew previously, subtracted 5. 1 minus 5 is indeed negative 4. So we end up with those same kind of values. So the shortcut then is just subtract 5. So 0 minus 5, 1 minus 5 is a negative 4, 2 minus 5 is negative 3. So this is our ending result here as far as what we ended up with. And so our, what do we say here, as far as our 0, 0, our piece over here, 0, 0, ended up moving to, that was the third line down, ended up moving to negative 3, negative 5. If we go ahead and take a look back then, there's our parent function, and then our bottom of the V did end up down here at negative 3, negative 5. So we showed that idea of how that ends up getting into place. So let's talk about vertical stretch and vertical compression. Okay, and so on this one, if I take a look at the square root function again, if I have the 2 outside my function here, this f sub 1 is just, I already had an f function up here somewhere else. I had to label a different f function so I can make it the square root of x. So that's what that subscript 1 is. No big deal as far as notation, just something to call your attention to. And so if I have the square root of x, we have the normal parent function. What we have here now is we have a 2 in front of the function. So it's not with x, it's the overall function. So I calculate a value for, I plug a value for x into f of x, I get a y value. So let's say I plug in 4. If I plug 4 in for x, I would get square root of 4, which is 2. Now after I get this 2, now I apply this multiply by 2. So what I'm going to do is I'm going to end up doubling all my y values. So if I double my y values, it's almost as though I'm standing on the y-axis here, and I'm taking my hands, I'm grabbing hold of this graph, and I'm going to pull it up. I'm going to stretch it up here. Let's see what happens. So I've got this 4, 2, okay? Now I'm going to stretch it up now to 4, 4. I'm going to take this 1, 1. I'm going to stretch it up now to 1, 2. I'm going to take over here, I'm going to take this 9, 3, stretch it up to 9, 6. Because if we notice, that's what happened with all these values. Each one of my y values ended up getting doubled. The other thing we think about on these are the compressions. Is if I'm standing on the y-axis, or excuse me, the x-axis here, I take a hold of the function and I push it down. If I push it down, I'm compressing it. Okay, so that's going to be a vertical compression here. What happens with all of our y values, every single y value ended up getting cut in half. So this 1, 1 here ended up becoming 1, 1 half. At 4, 2, now it becomes 4, 1. If I can land directly on it, there we go. Let's see, this 9, 3 here ended up being 9, 1 half, or 1 and 1 half rather, because half of 3 is 1 half. So what we see then, when we ended up with, and let me come back to my other screen, when we had values outside the function, it affected the vertical. Okay, so outside the function here, we moved up or down whatever the k value was. Now we're saying I am still going to do the same thing. Okay, I'm still outside the function. Since I'm outside the function, I'm doing something to the y values. So if I have something here outside, that affects my y. So this is going to end up being a vertical stretch. And the other one is going to end up being a vertical compression. Okay. And so I've already answered the question a little bit. How does a, f of x, differ from just y equals f of x? This is going to affect the up and down. Am I stretching it? Am I pulling it apart? Or am I kind of squishing it? Am I squeezing it together? So whatever that value is out front, that's going to be our compression. If we're into rules and we like the ideas on how to explain things, okay, if y equals a times f of x, what we do is we take our y values take y values, and then we're going to multiply by whatever a is. And if a is bigger than 1, it's going to end up being a stretch. If it's between 0 and 1, then we're going to end up being a compression. Okay? Now, what if we switch this around? What if I take the a that was here and I move it inside the function? Now we're not working on the y values. Now we're working on the x values. Okay? So whenever we have the x's, we always think about, oh, well, if my x is going to the right 2, I want to go left 2. So we had that idea here. Similar when we do our stretches and compressions. What we're going to do as far as our rule here, okay, if we have f of ax, we're going to end up multiplying each x coordinate or each x value. Now, because these are the x's, we have to think about what are we doing differently? What are we doing strangely? Instead of multiplying by a, we're going to multiply by 1 over a. Okay? And so this multiplying by 2 up here inside is going to end up compressing this function, okay, and we're going to push it back down, and this 1/2 is going to end up stretching it out, okay. So this is going to end up being the compression. This is going to end up being the stretch. Let's take a look at Desmos and see what that looks like. Popping over here. So we have, again, our square root function. Now, if this is 2 here, what we're saying is multiply every x coordinate by 1 over 2. So multiply every x coordinate by 1/2. So over here, what I have is I have 1, 1. What I want to do then is I'm going to end up multiplying my x by 1/2. So I'm going to end up with a 1/2 1 is what I should have. And that's what we have. Over here, we have 1/2 1, and corresponds to the 1, 1. So what happened to this 1, 1? It got moved over here to a 1/2 1. So we're taking this and we're taking these values and we're pushing them to the left. So we're squeezing it together. So that's a compression. If I take a look at 4, 2 here, 4, 2, going to multiply my 4 by 1 over 2, so multiply by 1/2. So now instead of 4, 2, I've got 2, 2. At 9, 9 normally is 3. Multiply the 9 by 1/2, which is 4.5. So now I'm at 4.5, 3. So again, whenever we work with our x's, so something inside the values there, inside the functions, we're applying to x. If we're working outside the function, we're applying to y values. And if we do comparison here, if I go ahead and take a look at the 1/2 x and square root of that, what I'm saying is let's take the y value, or excuse me, the x value at 1, 1. Let's take the 1 from the x, multiply it by 1 over 1 over 2. So that's the reciprocal. So the reciprocal of 1/2 is 2. So now instead of being at 1, 1, now we're at 2, 1. Likewise, instead of being at 4, 2, if I multiply the x coordinate of 4 by the reciprocal of 1/2, so multiply by 2, it should end up with 8, 2. Okay, and that's what we end up with over here. We end up with 8, 2. So we end up multiplying by the reciprocal anytime we have these items over here. So this 1/2 here, I took the function and I stretched it out. When I had the 2, I ended up compressing it. So just the opposite of what we saw with the verticals. All right, so those are some examples as far as what we're doing with our overall values, what happens with our vertical stretches, vertical compressions, and overall those kinds of items. So let's do an example. Let's take a look at this particular example from the textbook. It's example number 8. It says the graph of y equals f of x is given in figure 60. So I've done a graph of it over here. I didn't like the one that was in the textbook, so I went ahead and put it in Desmos and plotted some points in here. Use this graph to find graphs of y equals 2 times f of x, and then y equals 3 f of 3x. So one of these, we see that whoops, there's no highlighter. We see that my value I'm multiplying by is outside the function, and the other one we see the value we're multiplying by is inside the function. So the one that's outside the function is going to affect y, and the one that's inside the function is going to affect x. And that's how we always think about these. If f of x is the y value, so I've already calculated the y, now I'm going to multiply it by 2. So really what that means then is this is going to, let me color coordinate back again, sorry about that. This is going to end up being then a vertical stretch by a factor of 2. So every y value I have is now going to get multiplied by 2. So it's 0, 0, the 0 stays at 2. Pi over 2, 1, now my y value is going to get multiplied by 2, so it's going to be up here at 2. At pi 0, 0 is going to stay at 0, because 0 times 0 is 0. 3 pi over 2, negative 1. If I multiply negative 1 by 2, I'm down at negative 2. 2 pi 0 is going to stay at 0. 5 pi over 2, 1 is now come up to 2. And the 3 pi over 0 is going to stay at 0. So what I end up with when I connect those is another function where I've stretched this function out by a factor of 2. So wherever it was, I'm stretching it farther. I'm doubling each of my y values and seeing what happens to it. And so sometimes when we get into, not sometimes, but when we do get into later on in mathematics, and we take a look at our wave functions, that number that's in front is simply what we refer to as the amplitude. Okay, and so the amplitude, how high and low is this graph going to end up going? Okay, so that is our vertical stretch by 2. Let's see our f of x, or f of 3x rather. So on this one, what we want to do is we want to multiply each x by the reciprocal. So we want to multiply by 1/3. So I want pi over 2. So if I have pi over 2, 1, after this multiplication by a third, I'm going to end up with, whoops, sorry about that. Let's get caught up here. There we go. Let's see, I'm going to end up with pi over 6, 1. At pi 0, I'm going to end up with pi over 3, 0. Let's see, our next point was 3 pi over 2. So 3 pi over 2, 0 now becomes 3 pi over, see if I multiply by 1/3, 3/9. Okay. Whoops, well, I just messed that one up. I went to 3/6. There we go. I multiplied the numerators to the denominators. It should be 3/6, but 3/6 is the same as a half. So this then could end up being pi over 2. And then, let's see, 3 pi over 2, then we've got 2 pi in there, 2 pi 0. Whoops, I'm sorry, it's 3 pi over 2, negative 1. My mistake. So I need to make that the negative 1. This value over here, negative 1. And then 2 pi 0 becomes 2 pi over 3, 0. Up to 5 pi over 2. There we go. So let's see, 5 pi over 2, 0 now becomes 5 pi over 6, 0. I did that same thing again, didn't I? 5 pi over 2, 1 is what it should have been. Okay. If we were in class, I would have told you in person, hey, we all make mistakes once in a while. You go ahead and go back and correct it. You don't make a big deal out of it. You don't beat yourself up over it. You don't quit because of it. You just recognize, hey, I made a mistake. Let's go back and fix it and see what we end up with. And then we end up with 3 pi. I was going to write 3 pi over 0. That would not have been good. It's 3 pi comma 0 multiplied by a third. That would be pi 0. So as we take a look at this graph in here, notice what I have is as far as my x values here, my x coordinates, okay, I've got sixes, thirds, halves, and whatnot. And my last value here is just pi. So we're going to take this blue curve here. We're take that, and the farthest point is going to end up going no farther than right there at pi. And so as we take a look at that, um, one of the things that we might also do is get a common denominator. So that pi over 6, pi over 3, pi over 2. So the common denominator is going to end up being something over 6. So this is going to be stay the same as 1 pi over 6, 1. This would be, let's see, pi over 3. So over 3 would be 2 sixths. This 1/2 would be the same as 3 sixths. 2/3, if I want sixes, would be 4 sixths. 5 sixths would just stay the same, so that's going to stay the same as 5 pi over 6. And then, let's see, this would be, well, 6 pi over 6 if I want to go ahead and write it as sixes. Oops, missed another one in there. I want to make all of those y values 0 for some reason. Okay, so as we do this, so we want the sixth, and so let's see, I'm going to have a 1 6, 2 6, 3 6, 4 6, 5 6, 6 6 overall. So to take a look at this, if I just come back in over here, remember this, the shape overall comes up and down, up and down. So it's going to still stay the same as 0, 0. And then it's going to come up here as high as 1, back down to 0, back down to -1, get to 0, positive 1, back down to 0. So this graph is now going to change and look like this. So what I did was I took this graph and I really squeezed it on down and through there. So I squeezed this down overall. Oops, screen's kind of acting a little odd there. Squeeze this all the way down. And so I ended up with this item that did take 3 pi to have this up and down movement. I moved that up and down movement into just a single pi. So that's an idea of a compression. So we compressed this function overall. And how do we do that? The idea of working with the vertical, excuse me, the horizontal, because we're working with the x's, is to multiply by whatever this value is, take its reciprocal, 1 over 3. All right, that's probably one of the hardest ones to wrap our minds around. Anytime we're working with the x's, we have to do some sort of opposites. That always ends up being, for some reason, that more difficult component overall. Now we end up with some relatively easy ones comparatively. Let's reflect over the x-axis and reflect over the y-axis. If I have a function, f of x equals negative of x squared, let's go ahead and graph that, find the domain and range. So if I just have my normal function here, and I graph x squared, so I'm lose x squared, and so if I do my table of values, x and then x squared, -2, -1, 0, 1, 2, then we got 4, 1, 0, 1, 4. What we're doing then is we're saying, okay, let's now do negative x, whoops, negative of x squared. So notice where the negative is. It's outside the function, okay? Outside, so it's this and not this, okay? So if it was inside, that would do something with the x values. Since it's outside, it's doing something with the y values. So let's see, what I'm going to do then, if I plug in -2, what I end up with is the negative of -2 squared. So the square of -2 is 4, and put the negative, so that's -4. Plug in -1, plug in -1 there, and I have the negative of -1 squared. So the square of -1 is 1, and then we take the negative of that value. 0, well, negative of 0 squared is still going to be 0. That's the easy one. Then we get 1 and 2 back down through here. So we get the negative of 1 squared. So 1 squared is 1, and then negative. And then negative of 2 squared. So 2 squared is 4, and then the negative makes -4. So if we compare what happened to all of these y values and then what happened to them, they all ended up getting opposite values, so they're all negative. So we should end up with something like this. should end up going across the x-axis, and that's what we were looking for. If I take a look then, let's see this example 9 here. Here's x squared. I take the negative of x squared. I do see it's a reflection over the axis, over the x-axis specifically. Okay. Now, the other thing that could have done here, if I would come back up here, let me just do this for a moment, just so we can see. If I put the negative with the x, okay, well, that didn't look a whole lot different than what we had before, right? So if I just have x squared here, what's the difference between x squared and the negative of x squared? We see there doesn't seem to be any difference at all. Okay. Now, technically what happened, though, is because we put the negative inside with the x, we reflect it over the y-axis. Not as easy to see when we're already symmetrical over the y-axis to begin with. So what I want to do then is let's take a look at example number 10. This is going to be easier to see. The square root function, again, we're only defined for those values on the right side of 0, the values that are positive. So square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. If I put the negative inside of those, okay, let's see what happens here. Square root of negative of x, okay, now we've reflected over the y-axis, okay. So if I have negative 1, the negative of negative 1, okay, that's how we can do this. The negative of negative 1 turns positive 1. The square root of positive 1 is 1, but my x value was negative 1. So at negative 1, I end up being defined here, which is a little bit odd. Let's go back to this description over here. And so what we see, let me grab my pen here again. So we've got x and then the square root of x. So normally we can only do things like this, where we've got 0, 1, 2, and 3. But now I've got x and the square root of negative x. So if I plug in 0 here, I'm still okay, that's 0. If I plug in 1, though, then what I end up with is the square root of negative 1, and that's undefined. That does not make any sense. I cannot do that. And so that becomes problematic for us. So what we have to do then on this one is if we take negative 1, so we reflect over the y-axis, okay? So if we think about it this way, now 1, 2, 3, reflecting over the y-axis, then moves them back over here to negative 1, back over here to negative 2, back over here to negative 3. So if I reflect over the y-axis negative 1, then I end up with the square root of the negative of negative 1, which is the square root of 1, which is 1. If I take negative 4, then I end up with the square root of the negative of negative 4, which is the square root of 4, and that becomes 2. And if I plug in negative 9, I end up with the square root of the negative of negative 9, which is the square root of 9, which then ends up being 3. So it seems as though overall, when I do this one, my domain is just the opposite of what I normally have. So normally, let me do it down here. If I let f of x equal the square root of x, my domain has to be, we go from 0 out to infinity. But now, let's call this g of x just to change it up. If I've got the square root of negative x, my domain reverses and it goes from negative infinity up to 0 because I'm reflecting over those y values. All the values out here now get flip-flopped and they turn over here, they flip at the 0 mark. So now my domain on this one is negative infinity to 0, and my range still stays the same. My range didn't vary any. It's still going to go from 0 out to infinity. Okay. All right, so we did it. We did all of our transformations. As we take a look at our transformations, if you like rules and nice way to summarize everything, if this is in the textbook, I've also got it listed here. All of our shifts, horizontal and vertical, are compressing, okay? as far as horizontal and vertical compressions and stretches. And then we also have our reflections about the x-axis, reflection about the y-axis. So we've made it through section 3.5, techniques on transformations. I hope this made some sense. If you have questions, please let me know. If you notice I made a mistake, also please go ahead, contact me, let me know so I can go ahead and fix that. So if we'll see you in the next video, which should be, I believe, section 3.6. That would make sense if this was section 3.5.